Okay, today's lecture is on more dynamic programming. I hope you're getting the hang of it after doing some of the problems in the homework, right? So I want to do some more advanced examples of dynamic programming, including some nice problems that are useful in practice. And also to reinforce the ideas, right? So here is a simple variation of the problem we saw last lecture, right? So one of the examples we saw, which is nice, is that if I give you a string, I want to know is it in L star. What does that mean? I have a language L, like think of it as English, and I give you a routine which tells you whether a given string is in the language or not, right? Take English again as an example. Is this string in English? We know how to do that somehow. And we wanted to answer the question, is a given string in L star, right? That means can I split the given string into strings which are, each of which is in the given language L, right? So I'm going to add a small extra constraint for you on this, where I say, okay, I want to know, I give you another integer parameter k, and I want to know is the given string in L to the k. Okay, what does it mean? Can I split my given string into k strings, each of which is in the language? Okay, so I don't allow you to say, use, so let's look at an example, right? So is this an English sentence is a string, and I want to know is it in English to the 5. What does that mean? Can I break up this string into 5 strings, each of which is in English, right? Not like any number of strings. I'm not allowing you to use any number of strings, right? Okay, so can we do this? Is this an English sentence? That we can do because there's like five strings, each of which is in English, right? Yeah, so the answer should be yes for this, right? So, but what about, is this an English sentence? Is it in English to the 4? Probably not, right? Unless, right? Okay. So, what about this one? Is it in English square? Why is that? No, that's not the meaning of English square. Yeah, English square means that this should be written as concatenation of 2 strings, each of which is in English, right? Okay. Yeah, this can be right because it is asinine and at, right? Yeah? Okay. I just made up. But is it in English to the 4? Yes, right, because it's as, in, it, right? That's the difference. So it's both in English square and English to the 4, right? And okay, this is an example which is not in English to the 1, which is just English, right?
So
okay.
Back to last class.
Yeah.
Is this an English sentence? Is that in English 1?
No, that was English star. I didn't care how many you split it into. Here I'm saying, no, I don't want you to split it into more, not more, I just said I want you to split it into exactly k, right? So it's a constrained version of what we already saw, right? So I want to show you that dynamic programming can handle this too. And so that's the power of DP, that you can solve this kind of problems too, right? Okay, so how do we solve this problem? So when is a string in L to the k? Okay. Okay, my claim is, well, if k equal to 0, W is in L to the k if and only if W is epsilon, right? If k equal to 1, W is in L to the k if and only if W is in L, right? If k is greater than 1, W is in L to the k if and only if W is UV where u is in L and v is in L to the k minus 1, right? Just take the homework, yeah, it's right, yeah, a little bit, that's why it was chosen, right? Okay, but it's a little bit. I mean, see earlier, L star just said, W is uv where u is in L and v is in L star, right? Here now there is a parameter k which decreased, right? Okay, so the sub problem we need to solve is no longer the original problem, no, of L to the k, but now it is L to the k minus 1. So our problem is you need to enrich the space of things you need to consider where k is also a parameter now, right? K decreased, right? Yeah. Okay. So the sub problems that you're interested in is no longer just depends on L star, right? So we can write a recursive algorithm based on this, right? Just using this thing. Is string in L. This is L to the k, I just put Lk here. What are the inputs to this routine? A string, right? And the integer k, right? Okay. So the recursion both involves the string and now k as well, right? Okay. So if k equal to 0, then when should we say yes? If n equal to 0, right? That means that the string is empty, yeah? Then output yes, else output no, right? If k equal to 0, the string is long, we should output no, right? Yeah. If k equal to 1, we check whether the string is in the language. Yeah. Okay. If else, what do? You break up the string and see if you can break it up, right? Into what? You check whether the prefix is in the language and the suffix is in what? With the language L to the k minus 1, yeah? Okay, all right, yeah, simple enough. Okay, now the thing is, here we are recursing both on the string and k, right? Both parameters, it's a two-dimensional recursion, right? Okay, that's the only small change, right? Where we have two things that we are using in a recursion, yeah? But in a simple example. So now I can ask the question, if I start with a string of length n and k, what is the structure of the sub-problems that is generating? So as I do the recursion, what are the sub-problems looking like, right? Is there how many of them are there? Can we understand them? So we are recursing here, right? This is, each recursive problem looks as what? Oh, that's just the array from I plus 1 to n. The notation is that this is, I'm giving you, I'm looking at the sub array from I plus 1 to n. Yeah, sorry, yeah, okay. No, it is okay, Let's look, okay. That's my attempted parenthesis, okay. All right, it's I plus 1, right? Yeah, agreed? So, okay, my claim is that each of the subproblem is a suffix and some integer which is between 1 and k, right? Or 0 and k, yeah? So, the number of subproblems is only n times k, no? And we understand the structure of it, yeah? Okay, so we generate O of n k subproblems, right? And each of them can be, how much space, you can have to allocate that much space, right? It's a two-dimensional array now because we have two parameters. And so we need that much space. What is the running time though? What is roughly the running time of this algorithm, crudely? If I just memorize it, how much time you think it will take? Yeah?
Memorization would only be useful if
Yeah, I know, but even then, what if I convert it into an iterative algorithm, what would be the running time is what I'm asking. Yeah, you had an answer? Yeah. Is that right? How much work are we doing here? So you have to do n work, right? Because you have to check all the prefixes. To solve one problem, you need to do n work, right? Because for I equal to I want to n minus 1, you have to check E string in L and check whether the suffix is in k minus 1. So one guy has had to check n of these, right? So, right, it's not enough to check. The amount of work in each recursive call, assuming all the previous problems are available to you, is n, not 1, right? Because I have to check all possible prefixes. Is that okay? So look at this recursive call. What is it? How much work is it doing, assuming that this is constant time? It has to do this loop, no? Yeah, n time it has to take roughly, right? No, not n over k. Why would it be n over k?
Because that's a unique.
N minus k, maybe. You want, but roughly n, no? You can't, I mean, yeah, no? Is that okay? Or am I, is this confusing? Yeah? I have to check all the n prefixes, no? To know the split. Yeah? Any question on that? No, it's confusing. Okay, I claim that you need to spend basically, if you don't do any further optimizations, you have to do n work per each problem, right? Because you have to check. So it is n square k. No, you said you're right. I didn't say you're wrong. Okay. Okay. I'm saying crudely, right? If you didn't do optimization, you could still figure out the running time by still looking at the code, right? And say, aha, even if this were available to me, I have to do n work. And there are only nk problems, I have to do n work for each problem, so it's n squared. Yeah? Yeah? All right, okay? That's it. So DP can do this kind of extra parameters, right? Maybe I want something else, some other bell and whistle on how many I have to split and things like that. You can make the parameter part of your recursion, and it increases the running time, it increases the space, but you can incorporate complicated additional constraints into the dynamic programming appropriately, right? This is one example. Yeah? No, I didn't have any next slide. Here is a variation for you to think a little bit. So I said, I want to split it exactly into k, but suppose I say my problem was, can you split this string into some number of strings as long as it is not more than k? Okay, you can split it into 2 or 3 or 4 up to k. It's a slight different problem than what I did, right? Okay. Okay, so the change is I am allowing you to split up to k. Okay, so for example, if I gave you this, the difference is here it is asking is the string in L to the k. Okay, now I'm saying is it L to the at most k, right? So it can be L to the 0, L to the 1, L to L square up to L, right? Okay, so for example, this is in English to the 4. For example, if I gave you this sentence, this string, and say, is it in English to the 10? Your answer should be yes, because it's in English to the 5, and 5 is less than 10, right? So now, can you solve that problem? Okay, what is the easy way of solving that problem now that you know how to solve the previous problem? Run a loop and that changes k. That's good, right? Why reinvent the wheel, right? Okay. Okay, now only problem is what? How much time will that take? Sorry? It will take n square k times k, right? Okay. But my claim is you've already solved all that stuff in this recursion. Okay. While you are solving this k problem, you have in fact solved k minus 1, k minus 2, k minus 3, and all the way up to 0. So this problem is embedded inside your original problem, so you shouldn't spend any more time than what you needed to. Okay. So a good idea is to say, I know how to solve the k problem, I'll do it k times. Good. That's a good algorithmic thinking, right? Don't reinvent the wheel, right? We know how to solve the easier problem, or we already solved the one problem, and this is easy loop over k times, right? But then if you want to optimize, I claim that you've already solved this problem using the same recursion. Okay? Think about it if you don't see it. Okay, so you can solve it in the same. Okay. Okay, we know palindromes. This is a standard problem, right? If you ask you in the homework, you will basically Google it, right? So let us do it in how much time we spend trying to figure out problems that are not easy to Google? A huge amount of time, right? I mean, not because at some level I care. It's because if you don't do it yourself, then you don't learn, right? So I care in the sense of, and the temptation is so strong, no? You type and it's there, So we work hard. Here is a nice problem, right? Everybody knows what a palindrome is by now, I assume, right? So I give you a long string, and I want you to find a longest palindrome sitting inside that string as a subsequence. So okay, so this is some strange string, right? Okay, and inside that, this is a subsequence. Okay, it happens to be a palindrome. Okay, so I want to find the longest subsequence of the given sequence, which is a palindrome. Okay, is it okay? What I said? Yeah. If the whole thing is a palindrome, you should return the whole thing, right? Because that's the longest, right? But maybe it's not a palindrome. This is not a palindrome, right? Maybe it's not obvious, but it's not a palindrome, right? So think of it as a sequence, okay, sequences and strings, okay, this is not quite a sequence, it's a string, right? So I don't want to use a substring because substring means that it's a contiguous thing, right? So I want to use a substring. That means, you want to look at you pick the letters of this long string so that they form a palindrome, and I want the longest one. Is that okay? The problem is clear? Yeah? Or no? Everybody sees the problem? Yeah? Yeah, how will you solve this? Yeah? Yeah? Okay, so I give you this string. You want to say, maybe I like going from the other. You want to say, okay, if it is not if this is not part of the palindromic subsequence, what do you recurse on? The rest of the string, no? Okay, but if it is if you want it to be, what should you do? How can this be part of a palindromic subsequence of this? It has to have a partner, no? Yeah? I can't include this in my palindromic subsequence if I don't match it with somebody else. Yeah? Is that okay? Okay, so if I want to have M here, what should I do? I should look for a matching M, right? Yeah? Otherwise I can't include it, no? I mean, assuming it's not a string of length 1, right? So what M should I choose? Should I choose this M or this M or this M or first one? Okay, why? Yeah, so in that one way of thinking about it, but maybe you don't want to even optimize. You say, if I want to include this M, I need to match it with some other M, right? Yeah? Okay, so where is that M? I don't care. I can choose all of these, any of these, right? Okay, if I choose this M, what should I recurse on? What is the string I'm recursing on? If I match this with M, I have to find a palindromic sequence in the A to E, right? Okay. If I match it with this M, what should I do? I should match it, I should find the longest palindromic subsequence in from I to E, right? I mean, so it may be that you think intuitively that this M should be matched to this M, right? But maybe you're not sure, but you can try all possible ways of matching this M with any of this M, right? Okay? But in each of these cases, so you say, what is the new problem you're getting? Okay, is there any structure to it? Okay, so you say, aha, okay, If I don't include this, I'm recursing on m to e. That's one problem. Yeah. If I want to include m, I have many choices now. You know, I can match this m to m, then I recurse on a to e. If I match this m to this m, I recurse on I to e, right? If I match this m to this m, I have a problem from z to e, right? Okay? Okay, so I get many problems. How many am I getting? At most n, right? Yeah? Okay, but then they generate their own problems, right? Okay, how do those problems, do they have any structure? Are there lots of them or a small number of them? What kind of strings am I generating as I go along this recursion? Are they arbitrary? Are they prefixes? Are they suffixes? What are they? Are they arbitrary subsequences of the sequence? What is nice about the things that we are generating? I claim at any point we are only generating a substring of the original string. Yeah? It can't be like I'm dropping random things, no? I'm generating some substring of the original string, no? Yeah? Is that okay? Yeah? How many of them are there? Okay, finite is not good, it could be exponential, no? Yeah? We're all always in the finite world here. But, no, not necessarily true, but how many are there? If a string is of length n, how many substrings are there? At most n square, no? How many substrings are there? You know, it's defined by a starting index and an ending index, right? Okay. All right. Is that okay? That's very different from the number of possible subsequences, which is if you allow dropping, there are 2 to the n. Substrings are just contiguous pieces, right? There are not too many of them. Yeah? There are only n square substrings of a string, right? Okay, that's good because that's polynomial in n, right? So the number of problems that I will generate in this recursion is only n square. Good, we are done, right? Because at least we get a polynomial time algorithm now. If you memorize this recursion, we'll get a polynomial time algorithm. Yeah? Okay, what are the subproblems? ij, right? I want to know what is the longest palindromic subsequence of the from I to j. Those are the problems I get. Yeah? Okay? Is that clear? Yeah? It's a bit harder to see in this example, right? Because they are not prefixes or suffixes. But they're at least substrings, okay? So that's the thing that we need to get used to that. Intuitively after some, first I have to think recursively, right? But then you have to understand what are the problems that I'm generating. It's just a little bit harder here because they turn out to be substrings, which we're only used to prefixes and suffixes so far. Okay, but the number of substrings is also a bit larger, right? If I have a string of length n, there are only n prefixes and n suffixes, but the number of substrings is n square. Could be, up to n square. Yeah? Is it all right? Okay? It's a little bit more complex. So if you do memorization and all that stuff, you'll get something. Okay? I won't do the details of that. Okay? Yes? Yeah, thinking is always good, no? Okay, now let's do something, a very important problem in practice and in theory. This is called edit distance. To motivate it, let me do something called, many of us are used to these days especially, right? We start typing in Google and it start telling us what we should type, right? What is it, before, they use different techniques, but a natural question that comes up in spell checking, which is a very old problem, is how do you, if I have a string in English or something, how do you know if it is not in the dictionary, what is the closest word in the dictionary? So maybe we made a mistake in typing, right? And we want to know what is the closest word in the dictionary to something that we typed, right? If it is not in the dictionary, right? Because maybe we made a mistake in the thing, and what does it mean to find that word, right? This is a spell checking problem, right? So to make this more mathematical, we would like to formalize the notion of if two words, if I give you a word and I give you another word, I want to know what is the measure of the distance between them so that I can pick the nearest one, right? Okay, because it's not obvious, right? If I give you 2 points on the plane, you know, we have the Euclidean distance. Maybe it's different, I can define different types of distances between even points in the plane. I could be L1 distance or L2 distance or some other LP distance, right? So the same thing with strings. How should we think about the distance between strings that makes sense for the application at hand, right? Which is like, oh, okay, now, so given two strings, x1 to xn and y1 to ym on some alphabet, what is the notion of a distance that we can define? And in the context of spell checking, it turns out that one thing to think about is how many edits do I need to do to the string x to get to string y, right? That's called the edit distance. Yeah? How many things do I need to correct to go from string x to string y? Okay, so you know, here are two strings, food and money, right? And we define the edit distance. Okay, what are the edit operations we allow? To change the string, you can drop a letter, right? You can add a letter, or you replace a letter. Each of them is an edit, right? So you call, let's put value 1 on each of those changes, right? So how many edits do I need to go from one string to another string? Okay, is that okay? That's the notion of distance. It's not necessarily the best one or anything, it's just some notion of distance. So how do I go from food to money? I can say, aha, okay, I change F to M, that's one edit, right? And I introduce a letter N, right? That's one edit. And then I change O to E, that is one edit, and then I change D to Y as another edit, right? Okay? That's one way of doing it. Is it the best way to do it? I don't know, right? Maybe there is a shorter way to edit food to money, which only 3 moves. I don't know, right? Well, that's what we want to know, right? Given two strings, how do we find the smallest number of edits to go from one string to another string? Okay? If you had that measure, then we can solve the spell checking problem, right? I mean, at least inefficiently. Look at all the guys, or given a string, look at all the words in the dictionary and compute their distance and pick the nearest one. That is very silly, but at least it gives us some measure of what we want to do, right? Okay, so that's called edit distance, okay? But it turns out that this is not a convenient way of thinking about it algorithmically. Like, you know, one edit at a time is hard to do algorithmically. So we'll think about it equivalently as a slightly different problem as what's called an alignment problem, okay? So instead of thinking about sequentially converting food to money, we'll think of putting food on top, money on bottom, and aligning the strings in a way so that we can see what we're editing, okay? Okay, so how do we do it? So this is what's called an alignment in the following sense, right? We put F on M. What does that mean? We are going to convert F to M. That's one edit, okay? If O and O are together, we are not going to do anything because we are going to keep them the same. So we don't pay anything for the edit. O and N are different, so we have to convert O to N, okay? Here, there is no thing. What does it mean? We have to insert E, okay? D has to change to Y, okay? This is one alignment, right? What is the cost of this alignment? 1, 2, 3, 4, yeah? Okay? This is not the only alignment. I can do something silly, right? I can also say food, right? I don't know why I will do that, but what is the cost of this alignment? 5, right? Or is it 5? Yeah? Okay, I have to insert this guy, I have to change this guy, I have to change this guy, change this guy, and change this guy, right? 5. Okay, this is better alignment than this, no? Okay? Okay, so finding the edit distance is the same as finding the best alignment, right? Okay? So what is an alignment? Okay, an alignment is formally, you have to define it, you know, you have to I won't do the formal thing. I hope you can see the picture and you can look at the formal definition later, right? Okay, that you want to map each of these letters to a letter or a blank in the other string, and the right way you do it, you'll get a formal definition. Okay, let me not waste time on it when you can see it intuitively for now. Okay. Yeah, you can do. That's the more silly thing is, you can even do this, right? You can do this, right? I mean, that's also an alignment, right? What is its cost? That's probably, it'll be 9, right? That's allowed. Yeah? You want to find the alignment of the minimum cost, right? That's also a valid alignment. Yeah? Okay? Okay. So that's the problem, right? Okay, now I'm going to make it even more general because that's helpful to us. And this is where, so that's the problem. Given two strings, find the edit distance is to find the alignment with minimum cost. And this comes up in, this is actually part of the Unix diff and spell checkers and dictionaries. But the more important application in modern times is edit distance is used in DNA sequencing. Okay, that's a huge, huge application area in bioinformatics. Is how do you compare two genes or two DNA sequences using various complicated notions of alignment and stuff.
So the edit distance is not just the
No, why would that be, right? What if it is two are the same strings? The edit distance is what? No, it's 0 because you don't have to do any changes. No, the cost of, if I have these two things, it is just no cost to change O to O, right? You only pay if they are different, or if you have to insert, or if you have to delete. Yeah, it's only 4. Yeah, yeah, right. Okay. So in these applications, it's not. You need more refined function. Changing A to B is not the same as changing an A to C. Okay. So think about, a more refined model of edit distance. Suppose I'm typing, right? What is more likely for me to do, right? When I'm typing, what is a more likely mistake? It depends on the typewriter, no? Yeah? And maybe it also depends on me, right? That I tend to make more mistakes of certain type than other people, but at least we should take into account the typewriter, right? I'm more likely to mistype A with something closer to A than A with something very far away from, right? So how do we model that, right? Let's do the most general model possible, right? Okay. Sorry? Or you can do Markov chains or something like that. But here what we are going to do is a deterministic model where we say, if you want to change letter P to letter Q, you have to pay a cost alpha PQ. Okay, I tell you the cost up front. Changing A to B costs 10 units. Changing A to C costs 5 units. Changing A to something else costs something. For every pair of alphabet letters, I tell you the cost you have to pay if you want to change one to other. Is that okay? That's a very more general problem, no? Earlier we said anything costs 1. Now I'm saying I'm going to tell you the cost. It's given as part of the input. Yeah? And then also insertion has some cost, deletion has some cost, but let's say it's the same cost for inserting and deleting, right? Just to make our life a little bit easy. So that's called a gap penalty, which is if you want to insert or delete, you pay delta. If you want to map two letters P and Q, you have to pay alpha PQ. All right? Yeah? Okay. So that's the problem. Now even more general problem. And what is the edit distance case? When all the delta and alpha PQ are 1, right? Gaps and everything is 1, right? Okay. So here is some example, right? I have two strings, occurrence and occurrence, right? What is the cost I pay with this alignment? Well, see here, it's a more rich model, no? So here in this alignment, I have to pay a gap penalty for this C, yeah, delta, but I'm replacing A with E, right? Okay. So the cost I pay is delta plus alpha AE, whatever is that number I give you. Yeah. All right. What about this alignment? It is 3 delta, right? Yeah.
So delta is just for blank space?
Delta is for insertion and deletion. Okay. Okay. What about this? This is still silly, but it is 19 delta. Okay. Is it clear? Okay. So that's the model. Whether you like the problem or not, this is the model. Okay. All right. And so what is again the problem is I give you 2 strings, x1 to xn, y1 to ym, and all this costs, right? For every pair of letters, I tell you what is the cost to change this letter to that letter. And now you want to find for me the alignment with the minimum cost. Okay. But we are in DP lecture. Why are we thinking of graphs now? I mean, at least some contextual analysis, no? Yeah. Okay. Can we solve it recursively? Let's do DP, right? Okay. 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 So how do we think about this problem, right? Okay. Let's do some example. What is the edit distance between 374 and 473? 0. How can it be 0? They're 2 different strings. It can't be 0. Right? You know? 2. Okay. How did you figure it out? Sorry? Okay, you know, you can look at 2, right? You know, this alignment itself gives you a cost of 2, right? Okay, maybe is there better than that? Maybe, but maybe not, right? You know, if you have to do 1, you realize that you can't do it with 1. Okay. What about this, right? 1, okay. What about that? Yeah, I mean, assume that all of them are 1 unit, right? It's 2, right? Yeah. Okay, 2, well, you know. Yeah, okay. Is it 2 or 3?
3, right? Just tell me why the blank space.
It's 3. Okay, what is the alignment? You can align 3 to 4, 7 to 7, and so that's one cost, and then the blank is 1. Yeah. So it is this change and that change, no, only 2. Yeah, you shifted that too, right? Okay. Okay. So okay, that's the problem, right? You know, except that I give you very long strings where you can't see things. How will you solve it, right? Right? Think of your DNA sequence, right? And my DNA sequence. How will you figure it out? 1 billion pairs long, right? Okay. So we have to try to do it recursively. How do we do it recursively? Yeah, yeah. So, yeah, I mean, here is abstract picture, and we'll do a concrete thing, right? If you think of 2 strings, we are putting 1 string on top and 1 string on bottom, right? Okay, yeah. So what does an alignment look like? You know, okay, let's look at the last letters. I mean, some of you like the first letter. For some reason, I'm stuck on the last letter kind of approach, but you have to stick with some convention, right? What does an alignment do, right? To the last 2, let's look at the last 2 letters of the 2 strings. Either we match them up, right? Or we don't. If we don't, what can happen? Either one string is shifted to the left, or the top string is shifted to the left, or the bottom string is shifted to the left, right? Yeah? So let's see. Here is an example. Let's do an example before we do this. Okay, how should we align these 2 guys? What are the possible alignments of these 2 guys? 2 strings, right? We say, okay, you know, I think of, you know, D, E, D, and then I look at D, R, E, A, D, right? Okay. What are 3 possibilities? We align this guy with this guy, right? Yeah. In which case, what should we do? We should, then we forget about that, we are done with that, and we align these 2 guys, right, together. Yeah? Yeah, did we make this problem simpler because we have made both strings smaller, no? Yeah. What is the other thing we could do? We say, okay, and we say, okay, we are not going to align this with anything, we are going to align it with space. Yeah. In which case we have to align this with this, no? Yeah. Did we make both strings smaller? No, but we made at least one string smaller, no? Yeah. Okay, what is our third case? No, we align this guy with a space, right? And then we have to align this guy with this guy, right? Yeah. Those are the only three possibilities, no? For the last two guys, yeah? What else can you do? No, but that case is covered by that, no? See, so that be careful, right? You know, if I shift all of them, that's also allowed, right? But then the D is allowed, yeah, I mean, it is covered by this case where you are mapping DEE to DREAD, right? Yeah? Top D matches to blank, or top D matches to the bottom D, or bottom D matches to a blank. Yeah, these are the only three possible assignments, right? Yeah? So, it's also clear that, you know, we try these three things and pick the best alignment cost out of these three things. Yeah? So in each of the cases we have reduced the problem a little bit, no? And we can recurse. That's what it means to recurse, that we at least reduce one string size, right? Okay? Is that okay? Yeah? So if you do the plain recursion, what happens? We just do recursively solve this, right? What are the problems we are generating in this way? So we start with, you know, if we start with aligning those two, I create three problems, no? Right? What are the three problems? Aligning DEE with DREA, that's one problem. Yeah? Aligning, this case is I am aligning DEE with DREAD, that's one problem. The third case is I am aligning DED with DREA, right? And then I recurse again on that, right? Each of them will generate three problems on its own, right? Okay? So again, we have to understand what are all the different problems we are getting out of this. What do they look like? Each time we are aligning some string on top and some string on bottom. Do they have any structure? Yeah? What are this? What is the structure? No? It's not clear? I claim, because of the way we did it, that the top string is always a prefix of the top string, the original first string, and the bottom string is always a prefix of the original second string. Yeah? We are only generating prefixes, right? Yeah? Is that clear? See, if I start with DED and DREAD, in this recursion, at any any subproblem is of the form some prefix of DED and some prefix of DREAD. Is that clear? Yeah? Why? Because in the first step itself we created three problems, each of which is a prefix, right? Yeah? We are not generating some random things, we are generating prefixes of the strings, right? Because what is a prefix? It's DEE of the original strings. No, they're not saying. When I recurse, I'm trying to solving the problem of matching TEE to DREA, right? Yeah. What does a recursion mean? To solve this problem, I try these three cases and pick the best one, right? Yeah. Yeah. Yeah, if they don't match, no, you can match them, no, because the cost of matching them is given to me, right? If no, you can map them. Remember, we're working in the more general problem that if you match E and A, you pay cost, right? Even if they don't match in the edit distance word, you would pay 1. I can map E to A and then I would pay 1 for that. Yeah? Okay, I'm allowed to map them, it's just that I pay a cost for them. Yeah? Is that clear or not clear yet? Yeah? Yeah? Sorry, what is the? Before we understand runtime, we need to understand how many subproblems we generated from a string of length n and a string of length m. How many did we generate? N times m, right? Because it's a prefix of this and a prefix of this, right? So that's the different possibilities, right? Is that clear? Okay? And that's it. nm is a space, running time is nm because we are only spending 3 units of time. Okay? But we generate only 3 subproblems, no? Not many, just 3. We compute their values, pick the best of them. Yeah? Okay. Okay, no, that was too fast. Okay. Okay, let's go slowly. Okay? Okay, that was just as an example. So, recursively, how are we going? Let me recap it in a little bit more abstract language. We have 2 strings x and y. We can always write x as alpha x, beta y, where that's the last characters. Alpha, beta are strings, x and y are single characters. These are the 3 possibilities of aligning them, right? Okay? If one of them is 0, what happens? One of them is empty string, what happens? That's the base case. What is the cost of aligning a string with an empty string? It is the length of the other string times delta, right? Because we have to insert all of them, right? Okay, that's the base case, right? If not, both of them are not empty, right? That means that we can break up both strings into with last characters. These are the 3 possibilities for the alignment, right? And prefixes must have optimal alignment. And so we look at the cost in each case and recurse and compute the best of the 3 costs and output that, right? We don't know, we just do the obvious thing. And so we understand that we are only generating prefixes, right? So a subproblem by naming is of the form opt ij, where 1 to I is a prefix of the first string, 1 to j is a prefix of the second string, right? So what is the recursive formula? Opt ij is optimal cost of aligning x1 to xi with the string y1 to yj. Then opt ij is 3 cases. If we map the last 2 characters together, how much is the cost? We pay the alpha xi yj, right? That's the cost I have to pay, right? Whatever those 2 characters are. Yeah? And I recurse on opt I minus 1 j minus 1 because I make both strings smaller. If I map the last guy of the first string to a blank space, what do? I pay delta, right? And I shrink the first string by 1 because I already mapped the last guy. I pay opt I minus 1 j. If I map the last string, last character of the second string to a blank space, I pay delta and opt I j minus 1, right? I shrank the second string but not the first. Yeah? This is it, right? Okay? Questions on this? Okay? So the number of subproblems by just looking at this is n times m, and so the running time will be, and base case is opt of I0 is delta times I, and opt of 0j is delta times j. Right? If one string is empty, we just pay the length of the second string times delta. Yeah? Okay? Yeah? Okay? That's the thing. You can do all the thing like this, and okay, now you see that the subproblems automatically tell us that we should put what? A 2-dimensional array as our data structure, no? Mij should be our data structure, right? Yeah? So this is what it is doing, right? This is edit distance has a 2-dimensional array, 0 to m, 0 to n. We initialize all entries to infinity, and we do the recursion, let's not do the code because it's hard to understand. Let's do it as a pictorial thing, right? We are going to imagine this array as a 2-dimensional thing, right? 2-dimensional array. This is, we want to compute all of these ij entries, no? Opt ij, opt, so what is the base case? What do we know in this? Yeah, it looks like a graph. We'll see why it's nice to think of it as a graph later on, right? Yeah, I know, you're way ahead of the game. What can I say, right? Okay. So what is this? Do we know the values of all these guys? Yeah. Because one entry is 0, we know all the values, right? Opt 0, 0 is what? 0. What is this? Opt 0, 1. 1 times delta, right? So all this we know, right? And we know the column also, right? Yeah? Okay? So what do we want to calculate? We want to calculate this, right? Opt mn. What is opt mn? The entire m, the entire n, right? That's what we want to calculate. So we look at what opt ij is, right? What does it need to know? To compute opt ij, we need to know this value, and this value, right? Yeah? Because opt I minus 1, j minus 1 is this guy. This is I minus 1, j minus 1, I. Okay? So what order should we evaluate? We can do it either way. You can go this way, row order or column order, both will be fine. Okay? If you do row order, by the time we get here, we would have done all this row and also this guy, right? So we can evaluate this guy. Right? You do a column order, the same thing, right? We do column, column, column. We do this and this. Yeah? Okay? What is the total running time? We need to fill up a table of size mn. Each of them requires looking at 3 values and computing simple things. So it is constant time to evaluate one value. So the running time is mn. Okay? Space is mn. Yeah? Okay? Questions? Sorry? I didn't shrink anything. No, this is just a picture. What do you mean? This whole thing is an array of size mn. Right? It is an array, and this is just showing you the dependence. This depends on these 3 things in this fashion. Okay, this dependence graph is useful. This will come back to this later. Yeah. Yeah. No, so remember the base case is all these guys are known, right? Opt 0. If one entry is 0, we know the values of all these guys. So we can do this pre-computation. This is the base case. Both the column here and row here are base cases. And then once we know those base cases, then we can do row by row using the formula. See, what do we here, right? What is Mij? Mij is the min of 3 quantities coming from the recursion. Right? It's the min of I minus 1, j minus 1 plus alpha xi yj, delta plus mi minus 1 j, right? Shall I do an example? Yeah? Yeah? Just slowly, yeah? Yeah, you're given a table of what it means to change, yeah. In the edit distance case, they're all 1, right? Alpha xij is 1 if they're different, 0 if they're the same. Yeah? In the edit distance case, is 1 if they're, yeah? Any questions on that? You want me to do an example very slowly, or you see the picture? You're okay with the, yeah? You don't say anything, I assume you understood it. Okay. Yeah? Sorry? Yeah, it is good enough. Yeah. If a grader says something, Chandra wrote it in his slide, how can you say no? Right? You can do that. Yeah. Sorry? Yes. You may say, oh look, I am giving this code. Why do you want me to write the recursion, right? Yeah. You may say that. It's a valid question, right? But then if you give me an iterative code like this and don't explain anything to me, how do I know it is correct? No? Because inside this you have a recursive thing that you're thinking about. So then you have to prove it by induction anyway. So we are giving you less work to do by actually saying just write down the recursion so that we can actually evaluate the recursion. Sorry? You don't have to write the recursive algorithm, you can just write this, no? The rubric is telling you that you can simply write this. You can either write the recursive algorithm or you can just write this. Yes, otherwise how do you know your algorithm is correct? In the sense that either you give me an iterative algorithm and then you have to prove that correctness by induction, which will be basically the same thing, right? We are giving you less work by saying don't go through all the inductive proof, just give us the recursion which generated your iterative code, right? How do you know your algorithm is correct if you don't have something going on, right? Either you have to prove it by induction or you have to give me a recursion which generated that iterative code, okay? And also it's a pedagogical thing, right? You know, you may say, you may complain that I see the correctness immediately, so, you know, why do you bother me? Sorry, that's, right, it's, okay. Okay, now the next issue I want to discuss is, think of DNA sequences, right? M is 10 to the something, right? You know, huge length string, and N is a huge length string, right? So this algorithm is pretty slow, no? Mn is slow. You may say, okay, I don't know what else to do, but you may say there are two reasons why this is a problem in practice. Not only is the running time slow, which we'll have to live with, but the space is also large. See, if I give you a very long string, two very long strings like DNA sequences, which are quite long, now this takes quadratic amount of space, no? Right? Now space will be a killer. You can't even store it in your main memory to implement this algorithm, okay? Even if you're slow, the space will be a bottleneck rather than time actually, right? We are willing to wait one day, but if you don't have memory, what are you going to do, right? Okay? So, can we reduce the space of this computation without, you know, reducing the running time, right? Do we need Mn space? Yeah? So that is something you can do for very dynamic programming things. Here is okay. Here is a trick to save space. Okay. You see, what do we want to eventually calculate? We want to calculate this value, right? Why are we storing all these values anyway? We want this value. Why are we storing all this? Because to get to this value, we have to do all these computations, right? Okay. Okay. But my claim is that to get to this value, you don't have to store the entire table. It is enough to store 2 columns at a time and keep shifting those 2 columns. Okay. Okay. So how does this computation start? Suppose we know the base case. We know, say that we are doing column order. Okay. So we compute this column by base case. Then we compute the next column, okay, and then we compute the next column, and so on, right? Once you come to this column, do we need this column ever again? That's because we understand the recursion, right? This column is useless as soon as I move to column number 3, okay? When I go to column number 4, column number 2 is useless, right? So I claim at any point, it suffices to keep only the current last 2 columns so that we can move 1 column at a time. Yeah? Is that okay? So, to evaluate this final number, it is enough to keep only the last 2 columns in memory and don't have to store all the previous values. Okay? Is that okay? Okay, the same thing I can tell you, it is enough if you do the row order, it suffices to do only the 2 rows at a time. Which one should you pick? Whichever is smaller, right? Okay, M is smaller or N is smaller, you pick the right one. So the amount of space has gone down to linear space, no? If you have a string of length M and a string of length N, you are doing Mn computation, but because we understand the structure of the recursion and the iterative code, we can reduce the space from Mn to only M plus N. Okay, this is why we need to do this conversion from recursion to iterative code, because then you can look and say, aha, I can do some optimization, including space. Okay? Okay. So I won't write on the code, official code is there, but you know, it's an easy optimization once you see the picture, right? Okay. So space saving is very often possible to do in dynamic programming algorithms. Not always, but many times if you understand the structure of the recursion, you can do it. Okay? Now, then there's an important catch though to this. Okay? There's one important catch I want to mention because it's an advanced topic. if you actually compute the value, but I want to not only compute the value sometimes, I also want to compute the solution sometimes, right? That is the actual alignment. So if you throw away all these intermediate values, then you cannot recreate the solution. Okay? You'll get the final number, but you won't be able to recreate the alignment if you throw away all the intermediate values. Okay? So what do you do then? Okay? You have to take 473 to do that. Okay? Or you can read in the notes. Okay? It's a bit more advanced. Okay? So to actually recover the solution is hard if you throw away all the intermediate values. Okay? But you can do it. You have to be more clever. Okay? Considerably more clever. Okay? If you want to recover the solution in addition to the optimum value. Okay? It's not obvious. You have to do the recursion a little differently, and you have to combine, divide and conquer. You know, you have to do a bunch of work. Okay? All right? You can always kind of do it, but it's not obvious. Okay? So it's nice that you can look at the algorithm recursion, then you see the iterative code and you say, I can save space. And then if you want to come with the solution, you have to do that. Yeah, question?
The only reason why we can shrink it how we can, what if we got a problem where we can like directly relate it to something allow us to shrink?
I mean, the space that this way, I mean. Yeah, I mean, then we are kind of stuck. You have to understand it and see if you can do it. There will be problems which are complicated where you cannot do this obvious thing, right? But then it depends on the problem. You can't always reduce the space of a dynamic programming algorithm. When you can, it should be based on understanding the structure of the problem. That's what we try to do, right? If you just do the recursion and don't understand what the dependency is, then you won't be able to reduce space. But because I put the picture like this for you, you can easily see it, right? But that's part of algorithm design, to understand the structure more deeply so that you can do things like this. Optimize space, optimize running time, and things like that. Yeah? Sorry? Oh, you can backtrack, no? I told you, once you have the value, you can say, how did this value, the optimum value for this get generated? You can say, I came from here or there, and then you go back and say, where did that guy come from? You can backtrace. I didn't do it in detail, but you can. Yeah. If you stored all the values, you can figure out what is the right alignment. No, but you have lost all the information. No? Yeah, that's why it requires more work. Okay, that's a good thing. Okay, here is a problem for you to look at. So I want you to do it two ways, right? I give you two strings, x and y, and I want to find the longest common subsequence of that. So what is this? A, B, A, C, D, C, B, A, C, B, A, D. What is the longest common subsequence of these things? I don't know. Okay, you know what the problem is saying? See, AB is a subsequence of both of them, right? Right, because AB is here and AB is here, right? So, but that's of length 2. Can I do better? ABD. ABD is longer, no? Because ABD is here and ABD is here. Okay. Sorry? ABAD. ABAD, good, right? So ABAD is even better, right? So that's the optimal solution in this case. How do you figure it out? Okay, I want to do it two ways, but let me, the more fun way is to do the following. Okay, you can do like the kind of like the previous one, but I want you to use the previous one as a black box. How will you do it? Not shifting thing. See, you can redo the same recurrence kind of algorithm, it will work, but I don't want you to do it that way, okay? This is just for fun, right? This is why it's, I want you to set up these costs that are defined. Remember, for any two letters, you can set up a number, right? which is what is the cost of mapping that letter to the other letter. I want you to use those costs in a nice way so that you can just use that as a black box to solve this problem. Can you set up the cost between letters in such a way that solving this problem with those costs will give you the right answer for this? Yeah? Insertion and modification to be infinite cost, okay? Uh-huh. Mm-hmm. Yeah.
And the lowest cost, you can just figure out which one matches.
No, but you be more precise. That is a minimization problem. This is a maximization problem. So that itself should trigger something, right? This, remember here, we're trying to find the longest common subsequence. That is trying to minimize the cost of matching everything, right?
I think the longest subsequence is the minimization.
No, but according to what cost, right?
Cost of how much, what is that? There was a specific word called cost of all.
So, okay, so if you match A to A and B to B, I mean, so what should, I mean, how will we get the right cost, right? You know, so here, you know, think of this as an alignment problem, right? You know, A, B, A, Z, D, C, B, A, C, B, A, D. What do we want? We want A, B, A, D, right? So we want what we want is A, B, A, D is there, okay. We want A, what happens? A, B, A, D. Did I make a mistake? B, A, C, B, A, D. This is B, okay. That's why I was saying, where am I missing the, see, we want this somehow to magically appear from the other one, right? A little tricky. Remember the costs, I can make them even negative. They don't have to be positive. Yeah? Insertion deletion should be what? Yeah, zero cost. Okay. Yeah, that works, okay? Make insertion gap penalty 0 for letters which the same letter alpha A for any letter, you make it what? -1, for example, okay? And alpha, two letters which actually are different, you make their cost 0, okay? It's kind of weird function, huh? It is saying, you know, if you have the same letter, you get -1. If you have different letters, you have 0. Gaps are 0. Now you minimize the cost, that is maximizing the things that are common. Okay? It's really weird, but you can do it, okay? It's fun, okay? So all I'm trying to say is that you can do it by first principles, like exactly as you did. You can also reduce this because we solved not an arbitrary edit distance problem, but we solved a very powerful problem where I am allowing arbitrary costs including negative costs. We did not use the fact that the cost is negative or positive anywhere, right? So negative costs are also allowed, right? When you minimize something which is negative cost, you're maximizing something which is positive cost, right? That's what we need here, okay? So, or you can do it from first principles. You don't have to do it as a reduction. I thought it's fun to just show you that you can reduce it because you had this power to set the costs. That's the nice thing about solving more general problems than the one you need, because then you get this thing that you can use as a black box and you don't have to worry about, okay? Okay, I'll introduce one problem and then we'll do it next lecture because we don't have time. So far we have done dynamic programming on sequences because they're easy to understand, sequences, right? These are a little bit simpler objects. But dynamic programming is very powerful. It can do things more generally, right? And you can do it on trees and decomposable structures in general. Now, dynamic programming you can do even more complicated things, but you don't want to, I mean, in this class we'll only stick to sequences and trees simply because That's rich enough to have incorporate many applications, and you get the idea, and then you can do more advanced things later on, right? So okay, here is the maximum weight independent set problem that we already discussed, right? You're given a graph, and maybe you have weights, and you want to find an independent set which is largest weight. It's a hard problem. It's an NP-complete problem. Okay, so what do we do? And one of the things we would like to do is, okay, can we solve some special cases so that we can generate some machinery? It turns out that you can solve this special case optimally when the graph is a tree. Okay, why you care about that? Let's not worry about it, right? These trees seem so simple, okay, but they're still useful. Okay, so here is a tree, and I want to solve the same problem, right? The maximum weight independent set problem. And it's not actually obvious how to solve it. You can't use some greedy algorithm, it doesn't work. Okay, so what is the problem? I want to find an independent set in this tree of maximum weight. Okay, how do we solve it, right? Well, we could try the same recursion that we did for maximum weight independent set. What node would you choose to remove or include in a tree? Does it do anything interesting, right? What would you choose? Remember, how did we try to write a recursion for maximum weight independent set? We said pick arbitrary vertex. Either you are not interested in including that vertex, in which case you recurse on what? You throw that vertex out, make the graph smaller, right, because you're not interested in it. Or if you want to include that vertex in your independent set, what should you throw out? All its neighbors and itself, and recurse on a smaller problem, right? Yeah. So in a tree, which node is nice to pick? And does it do something interesting? You can either pick a leaf, which is natural, or it's natural to pick the root too, right? It's one of the two cases. You have to try both to understand it, right? So if you pick the root, what happens? Yeah, so the one case is you remove it. What happens if you remove it? You get, all these children separate out, no? The nice thing is, okay. Okay, so, but we think of it as one graph, but in fact it decomposes, no, nicely. Yeah? Okay, if I want to include the root, what should I remove? I have to include the root means that, I have to throw out the root and the neighbors, right? What happens when you do that? If I throw out the root and its children, what do you get? You get the grandchildren, right? Yeah? Okay, I have to solve each of the grandchildren. So if I do this recursively, what is it that I'm getting? So to solve the problem in the tree, I try throwing the root out, in which case I get two subtrees like this. Okay. The other case is I want to include the root, which means that I include the root, I have to throw out the children, in which case I'll get how many trees? This guy, this guy, this guy, this guy, this guy, right? Okay, now I have to recurse on all of them, right? Okay, when I do all this recursion, what am I getting? I'm getting lots of things, no? But are there lots of different things I'm getting, or am I getting a small number of things as I do this recursion? What are the sub-problems am I generating? What do they look like? So every problem that I generate looks like a tree rooted at one of the nodes, no? Things lying underneath, right? But there are only n of them, right? Will I ever get an instance where I say, I want to solve DH without I? I won't get that, right? I'll only get problems of the form a subtree rooted at one of the nodes of the tree, right? In this entire recursion, right? When I remove the root, I get A and this tree and this tree. When I remove RAB, I get this tree, this tree, this tree, this tree, this tree, right? When I recurse on this tree, I'll get H and I, right? So the only problems I generate are of the form a subtree rooted at a node of the tree, okay? And there are only n of them. So dynamic programming will work, okay? Yeah, work in the sense that as soon as you realize that the number of sub-problems is small, memoization will give you polynomial time algorithm, okay? So that's the nice thing about trees, right? They decompose. The thing about graphs is that they're complicated. Trees are simple, okay? So that's one more thing. Dynamic programming also works on trees because they're decomposable. Okay? So we'll see the details next lecture. Yeah, they'll give you one second. Okay. Yeah.
So for the problem with we should output